doing is problem 27 from chapter 1. 1 gallon of paint, volume of 3.78 times 10 to the negative third meters cubed, covers an area of 25 meters squared. What is the thickness of the fresh paint of the wall? So the volume and area, as I just said, and we're going to find the thickness, which I put as a representative variable of x. So to find this, we can deduce that the thickness is going to be equal to the velocity divided by the area, as in this equation. And then 3.78 times 10 to the negative third divided by 25 meters squared, plugged into a calculator, is 1.5 times 10 to the negative fourth. And that will be the thickness of the paint. For chapter 2 was problem 35, which states the driver of a car slams on the brakes when he sees a tree blocking the road. The car slows uniformly with an acceleration of negative 5.6 meters per second squared for 4.2 seconds, making straight skid marks 62.4 meters along all the way to the tree. With what speed does the car strike the tree? So we're given the acceleration, we're given the time, and we're given the distance of the skid marks. So first we're going to have to find the initial velocity to be able to find the final velocity, which is the speed that the car strikes the tree. So we set up an equation that puts the distance, and we find the initial velocity times time plus 1/2 the acceleration times time squared, so that way we can find this initial velocity. So you want to isolate it, so we subtract this over here to get this, and then we divide by t to isolate the initial velocity, and then we plug in the variables, 62.4, 1/2, negative 5.6, and then 4.2 squared all over 4.2. And then we get the initial velocity of 26.6 meters per second, and we find the final velocity by taking the calculated initial velocity, 26.6, and then add acceleration in time, negative 5.6 times 4.2, and the final velocity is 3.1 meters per second. So that is the speed that the car then strikes the tree, at 3.1 meters per second. Chapter 3 is 30. So in a game of American football, a quarterback takes the ball from the line of scrimmage, runs back a distance of 10 yards, and then runs sideways parallel to the line of scrimmage for 15 yards. At this point, he throws forward a pass downfield of 50 yards perpendicular to the line of scrimmage. What is the magnitude of the football's resultant displacement? So I started by showing a diagram, 10 yards backwards, 15 yards parallel, and then 50 yards the other way. So I made them vector components. So I put negative 10, I represents horizontal, j represents vertical, negative 10, negative 15, respectively, and 50. And then for the resultant vectors, I added them all together. And since I and I are two common variables, you add them together, so you get 40j as the resultant of x for horizontal, and then negative 15j as a resultant of the vertical y. So I write them in notation of the resultant total. Since it is a right triangle, use Pythagorean theorem, r squared equals rx squared plus ry squared. And then this would be like RZ, but it's just the whole resultant in total. So you square root it here to get a square root on that side to get r alone, equals square root of rx squared plus ry squared. So this is rx, 40i squared, plus ry, which is negative 15, and squared. If you square root the whole thing, you get the magnitude of magnitude of the displacement, which is 42.7 yards. Okay, for chapter 4, I did problem 55. A ball on the end of a string is whirled around in a horizontal radius of 0.3 meters. The plane on the circle is 1.2 meters above the ground. The string breaks and the ball lands 2 meters away from the point on the ground directly beneath the ball's location. When the string breaks, find the radial acceleration of the ball during its circular motion. Okay, so I drew a diagram, and I'm given the radius, where it starts vertically, where it ends up horizontally, and this isn't given, but it's the acceleration, which is just gravity. And then I deduced that the final position vertically is 0, the final position on the x, the final position horizontally is 0 because it goes right below, so it's not moving horizontally. It's not moving. Oh, the initial position horizontally is of course 0, and then the acceleration horizontally is of course 0. There's no forces acting horizontally. There's no forces acting horizontally accelerating. And then we're trying to find the radial, the radial acceleration, which is the circular motion. And if you're thinking of circular motion, you have to use this equation of v squared over r, which I'll employ later. So, because this, whatchamacallit, it's for when a particle moves in a circular path. And we use a kinematics equation to find what t equals, because we need to find the time. So we're using this equation where you have where it ends up vertically for the initial y. And then you're going to have the speed of y, which will be 0. So the time and the whole thing would just be 0 over here. This would be 1.2 as we have in where the y starts at. It starts 1.2 meters above the ground. And then we have 1/2, I guess wrote it as a decimal, times the acceleration in the vertical direction, which is negative 9.8 meters per second squared, times t squared, which is what we're going to find. And since the t's been canceled out, since this would be a 0 times whatever is 0, so 1.2, 0.5 times plus 0 plus 1/2 times negative 9.8, and then the t squared, which we're going to find. So we simplify it, then we get this, and then we subtract 4.9 meters per second squared and t squared over to get rid of the negative. Then we have t squared times 4.9 meters per second squared, so 1/2 divided by 4.9. Then we still have a squared over here, so we square root to get t alone, and then we have 1/2 over 4.9 square root, which equals 0.495 seconds. Now I ended up rounding that up in the next equation to about 0.5. So this is where we're going to find where it ends up horizontally on the ground. Where the x starts is at 0. Then we have to find Vx is what we're trying to look for. We're looking for the speed horizontally times t, which is now the 0.5, and then 0.5, and then we know that the then we have t squared, which is the 0.5 again, and then the acceleration in the x direction is of course 0, like we found up here. So it'd be, and this is the xf, which we also has up here. It ends up at 2 meters horizontally, so 2 meters equals 0 plus Vx, 0.5s, so these are 0 and 0. So we want to isolate Vx, so we divide 2 by 0.5. So the speed horizontally is 2 divided by 0.5, which equals about 4.0 meters per second for the speed. And then, so we take the speed, and then, and we're going to input it into this equation that we had earlier, which gives us this the equation when you have circular motion. So we have the speed squared over r, which is the radius, 0.3, we had earlier, meters. So the radial acceleration is 54.4 meters per second squared. It shows problem 47. A block is given an initial velocity of 5 meters per second on a frictionless incline with an angle of 20 degrees. How far up the incline does the block slide before coming to a rest? So I showed a diagram here with the normal force and gravity, and of course a force goes this way and one acts this way. But you need the total force is equal to the mass times the acceleration. So the mass and acceleration is going to be this mg sign right here, as that's what's acting against it. So it's going in the x direction, so it's a negative mg sine of theta, but it has to equal to the mass times acceleration. So to cancel out this m cancels out. So this is a negative g sine of theta. And whatchamacallit, a negative g sine of theta. And then, excuse that, sorry, that's supposed to be negative. And then this is going to be an equation to set up to be able to find the final position, which is the x of f. So this is going to be the velocity squared, which is going to be a 0 because it comes to rest. The initial velocity is the 5 meters per second, which was given. And then there's going to be 2 times the acceleration in the direction, which is going to be 9, the gravity times sine of theta. This is a negative 9.8 sine of theta times 2. This is a negative number. And then you're going to subtract this over. So that's a negative 5 meters per second squared divided by this is a negative. So the negatives cancel out. So it makes a positive on this side. So it's 5 squared over the 2 times 9.8 sine of 20 degrees is equal to the final position. So the final position is 3.73 meters up the incline that the block slides before coming to rest. I chose problem number 19. An adventurous archaeologist weighing 85 kilograms tries to cross a river swinging from a vine. The vine is 10 meters long and the speed at the bottom of the swing is 8 meters per second. Archaeologist does not know that the vine has a braking strength of 1,000 newtons. Doesn't make it across the river. So to start with this, I drew out a diagram, the length of the vine. I called it R, is 10 meters. I wrote out the speed which it goes, the breaking point, and the weight of the archaeologist. And I put the forces, the tension force goes up, and the force of gravity goes down. So I take force equals mass times acceleration, or in this case, it equals the tension force, and minus the gravity force, equals to, according to Newton's second law, the mv squared over r, the mass times the velocity over the radius, or in the length. So the tension is equal to this with this added to it to isolate the tension force. So it's mv squared over r plus mg. R is again the length of the vine. So I plug in with what I have, 85 kilograms times the velocity squared over 10 plus, oh, I forgot to put squared here, but imagine there's a squared there, plus 85 kilograms times 9.8, which is the gravity, and the mass, of course, equals 1,377 newtons. And since 1,377 newtons is greater than the 1,000 newtons at which it breaks, it means he does not make it across the river. So for chapter 7, I chose problem 55, which states a baseball outfielder throws a 0.15 kilogram baseball at a speed of 40 meters per second at an initial angle of 30 degrees to the horizontal. What is the kinetic energy of the baseball at the highest point of the trajectory? So that 0.15 kilogram baseball is thrown at a 30-degree trajectory, and we're going to find the velocity horizontally because the vertical velocity at its highest point is going to be 0. So we find out that it's going to be the velocity times the cosine of theta, which is going to be the velocity that was given, which was 40 meters per second, times the cosine of, this is going to be the cosine of 30 degrees, which is going to be 34.6 meters per second. And then we take the kinetic energy, with the velocity from horizontal that we were given, which is equal to the 1/2 mv squared, and we have the horizontal, which is the x. So we have the 1/2 times the mass, which is 0.15 kilograms, times the 34.6 meters per second squared, which equals the kinetic energy of 90 joules. So the kinetic energy of the baseball at the highest point of its trajectory is 90 joules.